more accustomed to the unexpected since COVID has struck. Okay, so before I jump into the definitions and some important concepts, can I talk a little bit about the focus of this class? This is good for you to know now because it kind of prepares you for kind of what to focus on and how to think about this class, which will help with being successful. So one of the things I emphasize is conceptual understanding of the concepts as opposed to just memorizing things. And you'll see that because the kinds of problems that you'll have will be applicational based, so you'll have to kind of apply your knowledge. To conceptually understand things, it kind of takes 3 ingredients. And so one is to memorize. That's kind of the first minimal thing. It's not sufficient, but this one thing that you need to do is you're going to have to memorize some stuff. Nearly every class period will have a few things. Sometimes there'll be symbols. Sometimes there'll be new terms that you'll have to just memorize. And so between that class period and the next, you should spend some time memorizing those things. And again, it's not overwhelming. It's just a few things. But it can make a huge difference because if you don't take the time to learn that material between the first, one class and the next, you come the next class period and I expect you all to know those terms that I'm using or the symbol, right? So that's one thing, is to memorize it. That by itself isn't going to get you anywhere because questions on the exams and things are not going to just be about you regurgitating things. You actually have to understand conceptually, but you do have to spend time doing that. And I really encourage you to make sure that when I introduce a new term or symbol or something that you learn it before the next class period. So that's one. There is some math in the class. I find a lot of students are kind of nervous about that because it's math. A lot of people are kind of math phobic. The good news is that the math in this class is a lot simpler than college algebra, which you've all taken. Okay, so the math itself is really quite basic. It's order of operations, so that's one thing you kind of need to know. If you have trouble with that, there's a review in the back of your book that you can kind of look at. But the order of operations that you multiply comes before addition, that kind of thing. Square root, squaring, addition, subtraction, multiplication, division, and that's it. Those are the things you need. Fractions, you kind of need to know a little bit about fractions, not much, but very little about fractions. We do use some fractions in the class as well as for ratios. Okay, and the last part, you need to spend some time thinking, kind of processing the information. Again, it's not enough to memorize. You don't want to just take a bunch of note cards and memorize a bunch of terms and think that you've got it, because you actually have to understand that stuff. So memorizing is important, but it's not going to get you there. So you kind of have to think of examples, and I try and provide problems on assignments and examples in class that are kind of intuitive, that foster that conceptual understanding, that you do have to put some time into really thinking it. And it's a good idea to get in the habit of asking yourself after you've studied something, do I understand it? Not do I have it memorized, can I spit out the definition, but do I actually understand what this means, right? Another thing that I emphasize is interpreting the outcome of statistical analyses. So you get the answer, you do the statistics, you get a number, but all of that is of no use if you can't describe to me what that means in that particular problem. Like, what does it mean that the standard deviation of number of children is larger in community A than B? What does that mean conceptually? Describe that to me. Of course, you can't do that now, but just being able to compute the standard deviation of those two communities and tell me what that standard deviation is and tell me that one is larger than the other, that's really not going to get you very far. You have to be able to describe in plain English, and you're going to see me say that all the time. Describe to me in plain English what that means. What does it mean to have a higher standard deviation in this particular context, right? And let's see, what's the last thing? Oh, how to choose the appropriate statistical analysis for the particular issue or problem. So one of the things that you're going to learn, and I'm going to emphasize throughout the course of the semester, is how to choose the appropriate statistic for a particular problem. So this can be if they have this particular research design, what kind of statistical analysis would be appropriate for that? And most of you are probably taking Psych 222 this semester as well. So that's the stat lab. You're going to learn in there how to do a lot of the stuff that we're doing in class here kind of by hand. You're going to learn how to do that with a statistical package where it's very nice. You just put in some information, you click around, and you get the answer without having to do any computations on your own. And that's great. But one thing about SPSS is it doesn't tell you what to do. It doesn't tell you which analysis to choose, right? So that's something that you need to learn how to do. Okay, all right. Okay, now some important concepts that'll lay the groundwork for where we go after this one introductory chapter. Population versus sample. So this is going to be very important in this class, especially later in the semester, the distinction between a population and a sample. So a population is the group of individuals that you're interested in learning about and extending your findings to. So this is in the context of doing research, right? So the population is the group of individuals you're interested in actually learning about and then extending your findings to. And sometimes it's all of humanity. Sometimes you're interested in something that would apply, for all of humanity, like the effects of positive reinforcement. This seems to affect all living organisms. When an animal receives a favorable outcome in response to behavior, that behavior tends to increase, right? Other times your population might be smaller. Some might be like people who suffer from clinical depression. So you might be interested in what kind of psychotherapy technique is most appropriate or best, I should say, is best for people who suffer from clinical depression. And so it's cognitive behavioral therapy or psychoanalytic therapy. Which one is more effective at treating clinical depression? Okay, in that case, the population is everybody who suffers from clinical depression. Or you might be interested in infants. How do infants learn? So that would be your population. And then your sample is just a subset of that population. So a sample is a subset drawn from that population. And it usually comprises the group of individuals that we do research on, right? So it's a subset drawn from the population, a sample, and we do research with samples. So I might take 100 individuals from the population, 100 individuals who suffer from clinical depression, and randomly assign them to receive either psychoanalytic therapy or cognitive behavioral. And then I follow them for 8 months and then compare their symptoms of depression to see if there's a difference between them. Right? And I'm not just interested in those 100 people. I'm not just interested in that sample. What I'm interested in is that population, people who suffer from clinical depression. I want to be able to, at the end of the day, be able to state whether or not there's evidence that one type of therapy is better than the other for the population, right? Not just for those 100 people that are in it. Maybe. And this brings us to the difference between descriptive and inferential statistics. I think the definition of that is actually on this sheet, the table sheet. So there's two major branches of statistics. One is descriptive. We're going to spend the first about third of the semester up to test one on descriptive statistics. And most college students, when they think of statistics, they're thinking of the descriptive kind. Okay, so descriptive statistics are used to organize and summarize data. The descriptive statistics used to organize and summarize data. So the average is an example of a descriptive statistic. Most of you are familiar with that concept of an average. We'll learn a lot more about averages later in the semester, but an average, for example, your GPA, right? That's an average, your average grade point average, right? And so it's a summary. It summarizes many different grades. You could have, 30 different grades in college, and we've summarized them. We've reduced them down to one single number, right, that summarizes that entire data set. Right? So the average is a form of descriptive statistic. You may have heard of a range before. If not, that's okay. But a range, how much for example, your grades, they could range from 3.0 to 3.3, very small range. That all your grades are within that area. So your range would be like 0.3. Where someone else, their grades might range from 1 to 4. So span a lot. Have a much bigger range. Inferential statistics is a more abstract concept, and we get to that after the first exam. Inferential statistics are when we use the laws of probability to determine the likelihood that the results in a study were just due to chance. So inferential statistics, we're using the laws of probability and, of course, the data that we've collected. We're using the laws of probability and the data we've collected to determine what is the likelihood that the results that we got in a study were just due to chance. It's just sort of a fluke, because that can happen. And if that likelihood is very low, and if the likelihood that the results were just sort of some kind of fluke is very low, that is when we're willing to make inferences, right? To make inferences from the sample to the population. Okay, let's go through an example real quick on this handout with the tables on it, with the data in the tables. Study 2, so this is study 2. Below are data from an experiment examining the effect of music on number of miles the participant ran. So effect of music on the number of miles the participant ran. Okay, so the independent variable is the presence or absence of music, and the dependent variable is the number of miles ran per week. Y'all see that? Okay, so music, the number was 5.8 on average. And so there are 25 people in the music condition, and they ran on average 5.8. So that average, that's the descriptive statistic right there, because I'm just summarizing the performance of those that were listening to music. And then those that were in the no music condition, the number of miles they ran per week was 5.2. So 5.8 versus 5.2. The music, those who are listening to music, ran an average of 5.8. Of course, a lot of people ran more than that or less, but that's the average, right? Versus 5.2 for those people that were in the no music condition. They ran on average just 5.2. And there were 25 people in both of those conditions. And we randomly assign them to one condition or the other. And so one of the things you learned about random assignment is generally when you randomly assign people to conditions, usually, on average, their individual differences should kind of balance out quite a bit, it's not perfect. Okay, so now based on that, we can see that there is what, 0.6 difference between those two in miles. So we can see that those people that are in the music condition on average ran a little more than half of a mile, more than people that were in the no music condition, right? Now at this point, we do not yet have real evidence that music affects how far people run. It may look like it, right? These are different numbers. That's certainly true. These people on average ran 0.6 miles more than those people. But I cannot attribute right at this point that half of a mile, a little more than half of a mile difference to the music, right? Why? Well, because these are just samples, right? It could happen. It could be that this is just some sort of a fluke. That I just happened to get some people in the music condition that just are more athletic, right? or they just, they just felt better that day, right? And maybe I had some people just by chance in this group that just hate running, right? There's all kinds of things that can influence how far people run. Music, I'm trying to figure out if music is one of those things. So with inferential statistics, what we do is we figure out, well, what is the likelihood that I'll get that much of a difference, 0.6 miles of a difference between these two groups based solely on a fluke, just by chance. How likely was that to happen? Because either this happened because it was just some sort of a fluke, that's one option, or this difference was actually due to music, right? Those are the two options, and I don't know which one is true yet. Just because there's a difference doesn't mean it was due to music, it could just be due to chance, right? So I figure out what is the likelihood that that difference was due to chance, and if that likelihood is very low, then I have evidence that that difference was due to music, in all likelihood. Now that all sounds probably very mysterious to you, like how in the world can we figure out the likelihood that that difference is due to chance, right? That seems very odd. Well, we'll get into that after test two. It's a lot of sophisticated ideas, kind of abstract, but we'll get to that later in the semester. But that's the purpose of inferential statistics. We're trying to determine when we are justified in making inferences to the population based on the results of a sample. Just getting interesting results in a sample doesn't mean that there's evidence that there's an effect. You can't just assume that. Okay. The parameter and statistic are another set of terms we need to know. So a parameter is a property of the population. And so population is a property of the population, some characteristic of the population. And it's usually something numerical that we can measure. So parameter is some sort of property, characteristic of the population. Like the average height of American male. Okay, so the population is all American males, adult, I'll say adult. All adult American males, and what is the average height? And there is some number out there. There is some truth to what that number actually is. I don't know what it is. No one knows what it is, but it's probably what? Somewhere close to what, 5'8", 5'9", maybe, something like that. But there is some number out there that represents that accurately. We don't have access to it. Why don't we have access to it? Well, we can't simultaneously measure the height of all American males in the population. We can't even, identify them, much less, measure their height. So we don't have access to that. A statistic is a property of the sample. So statistic is a property of the sample. So the statistic is the property or characteristic of the sample. So for example, the average height of American male in a sample, right? So instead of the entire population, maybe I draw a sample of 1,000 males, randomly select them from the population and then measure their height. And I'll get some number somewhere around 5'9". Alrighty, the statistic usually, if I've done a good job and you've learned about the ways to do good jobs and bad jobs and getting a representative sample, or randomly draw them from the population, if I have a good representational sample, then my statistic will come very close to my parameter. If I've done a good job, if I have a large sample and it's truly representative of the population, then my sample statistic will correspond quite closely to the parameter, the corresponding parameter. But it won't be perfect. The parameter actually is changing every minute. It's now a different number than it was when I begun this conversation, right? Why is it changing? Why is the number slightly different than it was 2 minutes ago?
People are dying.
Yeah, so people are dying, unfortunately. And new people are being born or turning 18, right? People are turning 18 all the time. So that number, very minimally, is fluctuating, right? You know, if we get far into the decimal points, right, they're fluctuating, right? So I can't get a handle on the parameter, but I can get a sample statistic, and that number can be very accurate, right? The discrepancy between a sample statistic and the corresponding parameter is called sampling error. Sampling error is that discrepancy in the amount reported by your statistic relative to your parameter. So the sampling error is the discrepancy or amount of error that exists between a sample statistic and the corresponding parameter. And we'd like that to be small. And there's things we can do to ensure that it's relatively small. Like one of the things is the size of your sample. Taking a random sample of 1,000 American males, pretty good. If I was to take a random sample of 10 American males, not so good. It's very easy for me to get someone who's really short or really tall. That would skew things, right? It would make, you know, if I got a really tall guy just by chance, it really, you know, that one individual would have a big impact on that average if there's only 10 individuals. Right? If I have 1,000, well, obviously I'm going to get some really tall guys, but also get some really short guys, right? And they all kind of balance each other out. Any one individual doesn't have that big of an impact when you have 1,000 people. So when you have small samples, on average, you're going to have more discrepancy between your sample statistic and your corresponding parameter. That becomes very important when we start doing inferential statistics. The size of your sample, as you'll see, is very important when we're trying to determine the likelihood of getting some sort of fluke. The likelihood of getting a fluke is much larger when you have small samples. So it's harder to be able to determine that your effect is real impact of, for example, music, if you have small samples relative to large. Okay, two main research methods. This I know is review. This is probably review from you from going back to 5th grade, right? Between experimental and non-experimental research. Maybe not, that's okay. But I know you covered it in research methods. Psych 220. So there are two main branches of research methods. There's a few others that don't fit nicely in there, but most 95% of the research you see out there published is of one of these two types. So experimental research and non-experimental research, or it's sometimes called correlational research. And one of the reasons why this is very important in this class is because the kind of statistics that you perform is very strongly tied to the kind of research you're conducting. You'll see that over and over again this semester. A couple of things about experimental versus non-experimental. This is kind of review, right? What makes something experimental? So I'm going to actually ask that. Sometimes it sounds like I'm being rhetorical, but yeah, so what makes something experimental?
Like it has an IV and a like something's doing it.
Yeah, exactly, yeah. So experimental research, something is being manipulated. The researcher is manipulating a variable, right? We call that the independent variable. So in experimental research, the researcher is actually manipulating a variable, right? Actually doing something. Like presenting half the participants with music and the other half with no music. And we call that variable the IV, the independent variable. I assume you know that. I use it all the time. I use IV, and I assume you know what an independent variable is, and it's the one that is manipulated. So that's unique to experimental research. And of course, then we also have a DV, and that is a variable that we measure that we think is impacted by the independent variable. Like in the study looking at the effect of music and how far people run, the DV is how far people run. We're trying to figure out whether the presence or absence of music impacts how far people run. Control over extraneous. A second unique characteristic of experimental research is control over extraneous variables. That research, you have much greater control over extraneous variables than you do outside of experimental research. So what this is scribbled on the board is control over extraneous variables. What's an extraneous variable? That's an important question, huh? Right, what's an extraneous variable? Right? If I say that we have control over extraneous variables in experimental research, but not in non-experimental research, then, well, what is an extraneous variable?
It's like another variable that will affect it. It's not necessarily in the study, but it's like another factor to consider.
Yeah. So an extraneous variable is any other variable that can impact your DV. Right. So all those other things that impact your DV. And with people, my gosh, there are always almost an unlimited number of extraneous variables out there. Sometimes they refer to that as noise, kind of an analogy, noise. I'm trying to determine whether or not someone is yelling from the other side of the room, whether that's happening, but there's all this noise and makes it more difficult to determine whether or not someone is yelling at me, right? Trying to figure out whether or not music impacts how far people run, but there's all these other factors that impact how far people run, right? That can obscure the effect of the music. I can't hear it, I can't determine it, right? Because of all those extraneous variables, right? So all those things that can impact your DV, and again, when we're talking about people are very complex. There's usually a ton of things that impact your variable of interest, your dependent variables. In this case, how far people run. And we're trying to determine whether or not music is the variable of interest. We want to see if that impacts how far people run, right? Well, there's a lot of things that impact how far people run. I'm not interested in those things, but they're there, you know? How athletic somebody is, how they're feeling when they run that day, their mood, how much they like to run, how comfortable they feel in an experimental setting, right? I'm bringing people in, putting them on a treadmill, asking them to run. Well, some people are kind of, shy or uncomfortable in this weird situation. They're not open to experience. All kinds of personality variables can impact how far people run. And of course, the most obvious ones are how athletic the person is, right? Whether they're a good subject or a reluctant subject, right? So there's, a lot of things that impact the dependent variable, right? When you have experimental research, we have a lot of, not complete, we have a lot of control over extraneous variables. So one of the things that we can do is that we can randomly assign people to conditions. We can randomly assign people to one condition or the other. We can't do that in non-experimental research. So another example is if I'm interested in the effect of playing violent video games on aggression. Well, if I do an experimental research, I can randomly assign people to play violent video games or not. And the good thing about that is that there isn't already some sort of selection criteria. If I do the alternative, right? If I study those two variables, playing violent video games and aggression, if I don't do that experimentally and I just ask people, I go, how many hours of these types of video games do you play? And some people will be 0, some will be 2 hours per week, some will be I spend 40 hours per week playing these types of video games, right? So I have a great variety of people playing a variety in terms of numbers of violent video games, and then I get some sort of index of their aggression level. Well, in that case, I don't really have any control over the extraneous variables, because it could be that people who play violent video games, they're going to differ from people who choose to play a lot of violent video games. Undoubtedly, they're going to be different in some ways than people who choose not to, right? And so I don't have that kind of control. Whereas in experiment, I have people, and I don't care what their interests are, right? I don't care if they want to play video games, violent video games or not. I randomly assign them to play it or not. So I have that kind of control. Right, so there's not pre-existing differences before I even collect any data. So control over extraneous variables. Also, I can do things like like control the setting, like I'm going to have people run while listening to music or not at a certain time of day, right? In a certain environment, like in a laboratory, where I can control all kinds of things. Right? Okay. And for those two reasons, I can make causal conclusions. For those two reasons, I can make causal conclusions. I have evidence that one thing caused the other, that music caused people to run more. Because if I'm manipulating a variable, right, when you manipulate something and then you wait for it to happen, right, cause comes before the effect, and I have that with experimental research. And I have control over extraneous variables, so I'm able to rule out alternative explanations for that connection. I have none of those things when I do non-experimental research. Right? I don't have manipulation of variables. I don't have any evidence of time precedence. Right? Time precedence, the cause comes before the effect. Right? And then also being able to control alternative explanations for the association that I see. And so non-experimental research, no manipulation of variables. I measure two variables. So I just measure two variables to see if they go together. No establishment of time precedence. I just measure two variables. How many hours of these types of video games do you play per week? And then get some sort of measure of regression. And then see if they're related. But because I don't have manipulation of variable, because I don't have any control of extraneous variables, if I do find a relationship, I don't know why. I can't say that one is causing the other. All right. So we just measure two variables, no manipulation of a variable, no control over extraneous variables. And so the kind of conclusions we draw are quite limited. You can say that two things are related. So that, for example, I might find that people who play violent video games, that they are a little bit more aggressive. I might find a positive relationship between those two variables, but I have no justification for saying that violent video games causes people to be more aggressive. I don't have that evidence. Right? There's too many alternative explanations. It could be that people are more aggressive, want to play violent video games. It could be that people who live in more aggressive communities or more aggressive families, or just, they tend to fight more and they tend to embrace violent video games, so it could be no association, a direct association at all. Okay, now that is probably all review from things you've heard in other classes. For statistics, the ramification here is the type of statistics we usually perform. With experimental research, usually what we do, right, because we clump people, right, because we're manipulating a variable, we have people that are running with music or not with music. Or we have people who play violent video games 20 hours a week versus action, but, I'm sorry, did I say non? They play 20 hours of violent video games a week, whereas this group played 20 hours of action-packed but non-violent video games a week, right? So I have the two groups. And so I group people, and then I compare the two means. So that's what I look at. So I compare averages between one group and the other. So for example, people ran on average 5.8 miles when they were listening to music, whereas they only ran 5.2 miles when they weren't listening to music. So my statistical analysis involves comparing group averages. With non-experimental research or correlational research, I typically don't have groups of people. I have how many hours of violent video games do you play? I don't just have people who play 20 hours a week and no hours per week. I have people who play, 0, 2 hours per week, 5 hours per week, 10 hours per week. They're all over the place. Right? And our dependent variable is a variable that takes on many different values as well. So I don't have different groups of individuals. I have two variables that both can take on many different values. And so the statistic I use is a correlation coefficient. Have you guys heard of that before? Correlation coefficient? It's okay if you haven't, we'll get to that. But it's a way to capture the relationship or association between two variables. So we use correlation. So use a correlation coefficient. And it's a single number that's computed from the data, a single number that captures the strength of that relationship between two variables. And it takes on a value between 0 and the absolute value of 1. So when we're dealing with experimental research, and because we only have a semester, we can't go into an extreme amount of depth in both types of experimental design. So we're first going to tackle this, and we're going to actually spend a little bit more time analyzing this. We're going to be looking at averages a lot, as you'll see later in the semester after the first exam. And then we'll get to correlation coefficient and correlational designs later in the semester. Experimental designs, typically a lot of looking and comparing averages, and with non-experimental designs, what we're looking at is correlational coefficients to capture the strength of the relationship between variables. Okay. That's okay. Okay, another really important thing to go over, and this is something I know you've gotten some exposure to in other classes, especially Psych 220, is scales of measurement, or nominal ordinal interval ratio. That might ring a bell. It becomes very important in this class because the scale of your measurement dictates the kind of statistics you can perform. So it's worthy of going over again right now. Get it, kind of make sure it's fresh in our minds as we proceed. So scales of measurement. And there's sort of 4 levels, and as you get further down, you get more numerical information. So at the top, most superficial level is nominal data. Nominal data. So nominal data is like categorical data, distinguishes one type from another, but there's no numerical information involved at all. So it's one type versus another type. So one type versus another type. You can't order them on a single dimension in terms of less than or greater than. They're just different. So like region of the country, you might be interested in relationship between region of the country and political affiliation, maybe. So region of the country. So I might have the West, the East, the Midwest, and the South, 4 regions. Well, one's not more than the other, they're different, right? So that would be nominal data. Sex of the participant, male, female. They're different types. Can't really order them from one is greater than the less than. Religious affiliation, so might have different, what is your religious affiliation? They're different types. Okay, so those are examples of nominal data. The next level up is ordinal. One way to kind of think about it is ranking. There is some numerical information with ordinal data, so you can align the values on a single dimension, can order it from less than to greater than. So ordinal data, think of it as ranking. So you can order it. One has more of whatever it is than the other. For example, placement in a race. You guys been to like the horse races before? Yeah, no? Yeah, most people haven't, but you've seen it on TV or movies. I know you have, right? You've seen horse races, TV shows or in the movies, so you know what it is, right? There's horses running around, right? And you have placements like first place, second place, third place. Those are the big ones, maybe fourth place, honorable mention. 5th, right, 6th, so they go down, right? And so you might have 10 horses, and so there's 10 placements. And so placement in a race, 1st, 2nd, 3rd, 4th, 5th, 6th, and so on. Well, that would be ordinal data, right? Because I know this horse came in first, right? Was before, took less time to complete the race than this one, and that this horse took less time to complete the race than that one. One thing that's important about ordinal data, though, and distinguishes it from the next one, is that the difference between score values is unknown, right? So there isn't a standard difference between the different scores on an ordinal scale. I do not know how much quicker the first horse was compared to the second, or the second compared to the third, right? There's all kinds of options. It could be that the first and the second were within a second of each other, right? And that the third one came in a whole minute later. Or it could be that the first came in and it wasn't until 2 minutes later that the second horse came in, that was just a second later came the third horse, right? We don't know that. All we know is the order with which they completed the race. So an important thing about ordinal data, we don't know how much more one is from the other. The next two are interval and ratio. I clumped them together because they share such an important characteristic. And in fact, SPSS software clumps them together as well for probably the same reason, I'm sure. So interval and ratio data. So it goes nominal, ordinal, interval, and ratio. Ratio has one other characteristic that interval doesn't. But both interval and ratio have very important characteristics, very important statistically, that is. And that is that the difference between score values is equal. So with interval and ratio data, the difference between score values is equal. One way to kind of think about that is, the word interval. Interval means a space between, right? So it kind of clues you in that that's important, the space between. The space between score values is equal. So, for example, minutes to complete a race. So minutes, right? Minutes is what I'm measuring, the minutes. Number of minutes, that is a characteristic in which the difference between score values is equal, right? And just think if I knew that for these horses, right? Because instead of measuring just a placement, I could actually time them in terms of how many minutes it takes them to complete it, right? And so maybe the first horse took 5 minutes to complete the race. The second one took 5.75 minutes to complete. The other one took 6 minutes to complete. The other one took 8 minutes to complete, for example, right? And now with this information, if I have the actual minutes that it took the horses to complete the race, I now have a much clearer picture of how long it took, right? That this one was a little bit more than a minute before the second horse came in, and this one was right, 15 seconds, quarter of a minute slower than that one, and so on. So the reason I know that is because the difference between the score values is equal when we're talking about the minutes, the number of minutes. Okay. What's the difference between interval and ratio, though? They both have that important characteristic, and in fact, number of minutes is actually a ratio on the ratio scale. There's more ratio scales out there than interval. The difference between interval and ratio is, in addition to both of them having that important characteristic, the difference between score values is equal, ratio has something called an absolute 0 point. It has an absolute 0 point, whereas the interval scale does not. So minutes of anything, to complete a race, minutes to play a piece of music, minutes that a class is in session, it's the number of minutes. It does have an absolute 0 point. Now, what is an absolute 0 point? An absolute 0 point is when there is a 0 on the scale, and that 0 actually represents lack of what is being measured. So that 0 means lack of whatever is being measured. So the 0 minutes, that means it took no minutes to do it. No time. So with a ratio scale, difference between score values is equal, plus it has an absolute 0 point where there's a 0 on the scale, and that 0 means that there is none of what is being measured. All righty. So interval. So length in inches, that's ratio as well. And if I'm measuring things length in inches, well, the scale, there's a 0 on that scale and represents the lack of distance, right? That's what inches is, it's measuring distance, right? And a 0 means lack of distance. So that would be ratio, length in inches, number of minutes. Weight. Weight in pounds is what we use in America, weight in pounds. Those are all ratio. One thing that's important to keep in mind is that when we're considering trying to figure out if it has an absolute 0 point, you're thinking only of the scale, independent of what it's measuring. Because you might think to yourself, well, obviously a horse cannot finish a race in 0 minutes. That's not possible. Okay, but we're not concerned with what is possible or what we are measuring. We're just concerned with the actual scale. Is there a 0 on that scale? Does that scale mean absolute lack of time? Well, then it's a ratio. So then interval. And here is an example of interval. Temperature, Fahrenheit. So the difference between 95 and 100 is the same as between 100 and 105. The difference between 100 and 101 is the same as the difference between 101 and 102. Does Fahrenheit have a 0 on that scale? Probably never experienced it firsthand, I hope, but yeah, there's a 0 on temperature Fahrenheit. But it's not an absolute 0. You can get colder than that, right? That does not represent complete lack of warmth. So temperature Fahrenheit is an interval scale. Temperature Celsius is also an interval scale. 0 does not mean there's a 0 in Celsius. And it actually has a meaning that's important, but it doesn't represent lack of warmth, right? You can get colder than that. Anyone here take chemistry? Chemistry, there is a scale that measures temperature, and it does have an absolute 0 point. It does represent lack of warmth complete. It's called a Kelvin scale. So there is one out there, but it's of absolute no use to us because actually things can get a heck of a lot colder than anything we've ever experienced or can probably even imagine. Okay. Let's see. Year 2021. What is year? Is your nominal ordinal interval ratio? Calendar year. What's that? Interval? Yeah, that's what I'm thinking. It's interval, right? The difference between square values is equal. Don't even throw out that whole leap year with me. Let's just pretend that doesn't exist. But just, we're being a little fuzzy about, yeah, that should be interval. Right? The difference between, between the time that elapses between 2020, right, between 2019 and 2020 is the same, right? 365 days, right? So it's, if you get really technical about it, you can probably tear apart this example a little bit, but let's not get really technical about it. But, the difference between square values is equal. There's a 0 on that scale, but it doesn't represent lack of time, right? So that would be an interval example. Okay, let's see if I can think of some more. Classification in college, so freshman, sophomore, junior, senior. So think about that for a minute. Freshman, sophomore, junior, senior, that classification. Is that nominal, ordinal, interval, ratio? Is it nominal? Can you order those classifications in any way from less than to greater than? Yes. So we know it's not nominal. It has more numerical information than nominal. Okay. So ordinal, it could be ordinal. Okay. Can it be interval? Is the difference between score values equal? Do we know? With No doubt. How much more a sophomore, how far advanced a sophomore is compared to a freshman? No, we don't, because you can have a freshman who has 29 credits, or a freshman who has 0 credits, right? Those are two very different things in relationship to what it takes to be a sophomore. Right? So the difference between score values is not necessarily equal. We don't know, if we know that someone's a sophomore and then someone else is a junior, we don't know exactly how much further along the junior is from the sophomore. And because of that, we know that can't be any more than ordinal data. So classification, that would be ordinal data. Salary. So someone's salary. How many, be nice, so hopefully they're making thousands of dollars a year. So their salary in thousands of dollars a year. What would that be? That nominal, ordinal, interval ratio. We know it's not nominal, right? Salaries and amount of thousands of dollars that people make per year. Okay, is it ordinal? It's at least ordinal, but the difference between score values is equal, right? The number of dollars, number of thousands of dollars, right? That's number of, just kind of a hint, if we're talking about number of anything that, it's going to be either interval or ratio. Does it have a 0 point? Can someone make salary of 0? Is that meaningful? Not that anyone does, although some people do, because some people volunteer or whatnot, but yeah, thousands of dollars. There's a 0, and it means that person's earning no money, right? Okay, so that would be ratio right there. Number of Facebook friends. You guys on Facebook still? Kids today, don't know what y'all doing. It's like TikTok, or I don't even know what that is. It's videos, right? It's like little videos. But can you follow someone's TikTok feed, or is that even the right term, feed? I don't know. Anyway, we'll go back to Facebook because I know what that is at least. Number of Facebook friends. Well, I kind of gave it away. I said number, right? So that would be a ratio, right? The difference between square values is equal. The difference between having 12 friends and 13 is the same as the difference between having 13 and 14. And there's 0. You can have 0 friends. It's not like MySpace when you started off with that guy Tom or whatever his name is. He doesn't even know what MySpace is. Probably. Do you know what MySpace was? Yeah. Oh, that's funny. Okay. Number of children. Well, I'm going to stop with the number. We know what that is. Let's see if we have something else. E's top 10 celebrity goofs. So the most goofed. Ordinal, yeah. Okay, yeah, because it's ranked. That's a silly example, right? But anyway, like the topmost celebrity goof, followed by the second, by the third. And so the first, the one that's ranked first is the biggest celebrity goof out there, right? So it's more of a goof than the second one, but we don't know how much more of a goof it is, right? Okay, that was not a great example. Okay, well, I guess maybe it seems like y'all have a pretty good. How about when we do political affiliation? Is that what? Is that nominal, ordinal, interval, ratio? I'm just going to stare at y'all until you tell me. So political affiliation, like, maybe this is too soon. Republican, Democrat, Independent, Green Party. Nominal, yeah, that's nominal. You're identifying different types, right? You can't really order it. There's not a natural single dimension by which you would order them, right? Because they're just different, right? You're not measuring quantity in any way. Okay, well, that's good. Well, that is what I wanted to talk about today. So thank you for coming. And I apologize for the technical difficulties. I'm going to try and get this room, and I'll be contacting y'all and letting you know if we successfully get moved to this room. And I will see you on Thursday. Probably Tuesday that you'll see something posted, like an assignment posted on Moodle for next week. But nothing for today.